In this lecture, we will see the schematic diagram of a 3-input NOR gate, and then we'll find the twistor schematic from the normal schematic diagram, and then we'll draw the layout from these two schematic diagrams. So at first, let's see the symbol and what is a 3-input NOR gate. It's a 3-input NOR gate. When I say 3-input NOR gate, then the number of inputs will be, then certainly my number of inputs will be 3. Is 3 and output is 1. Okay, so let the 3 inputs be A, B and C. The output is Z. So NOR means OR plus NOT. OR means A plus B plus C. NOT means the inversion of this, which will give A plus B plus C bar. So Z is nothing but A plus B plus C bar. This is A plus C, A plus B plus C bar. Okay. Since there are 3 inputs, so the number of PMOS and NMOS will be number of PMOS will be 3 and the number of NMOS will be also 3. When there is a plus operator, the NMOS is in parallel and the PMOS is in series. Now let's see the truth table of a 3-input NOR gate. The truth table of a 3-input NOR gate. It's A, B, C. So I can say it's A plus B plus C, then A plus B plus C bar. That is what the output of the NOR gate. Now this is in the table form. Put 0, 0, 0. When 3 inputs are 0, OR output is 0, and they invert, the output will be 1. When it's 0, 0, 1, the output is 1, not output is 0. 0, 1, 0, output is 1, this is 0. 0, 1, 1, output 1, 0. 1, 0, 0, output 1, 0. 1, 0, 1, output 1, 0. 1, 1, 0, output 1, 0. 1, 1, 1, output is 1, this is 0. So this clearly means that when all the inputs are 0, when A is equal to B is equal to C is equal to 0, then we'll obtain the output as 1. In all other cases, the output will be 0. Schematic of 3 input NOR. The schematic diagram of a 3 input NOR gate is, you know that the PMOS is in series and the NMOS is in parallel. So there are 3 inputs. So there will be 3 PMOS in series. This is VDD, and the 3 NMOS will be in parallel. This is ground. If this is input A, then this is input A, this is input V, and this is the input C. This is A, B, and C. Okay. So now this is P1, this is P2, this is P3, this is N1, N2, and this is N3. After labeling the PMOS and NMOS, now let's see which is the terminals, that is sources and gates. The source of PMOS is connected to VDD, and the source of NMOS is connected to ground. So this is source of P1, this is drain of P1. Now before labeling this is the gate of P1. We know that the output is obtained at the drain terminal. So this is the common drain. So this is the drain of P3. This is the source of P3. This is the source of P2. This is the drain of P2. This is gate of P2. This is gate of P3. Now labeling the NMOS will be very easy. This is gate of N1, gate of N2, and gate of N3. Output is obtained at the drain. So this is drain of N1. This is drain of N2. This is drain of N3. This is source of N1. This is source of N2. And this is source of N3. We know the sources of NMOS are connected to ground. Now, after seeing the schematic diagram of a 3-input NOR gate, now let's see the explanation for the truth table. That is, apply the input to the, this is the input A, B, C, and there is the output Z. This is the output. Output is obtained from the common drain position, or you can just extend this. Z is the output. One has to know why the outputs are obtained. The output that we obtain in the truth table, one should verify whether it is correct or not after implementing on the schematic. So let's see the explanation of the truth table. We'll see one by one condition. The first condition is when A is equal to 0, B is equal to 0, and C is equal to 0. When all the three inputs are 0, A input is given at the gate of P1 N1, B at P2 N2, and is at P3 N3. We'll see the twisted schematic later on. This is P3 N3. The input, if it's 0, then PMOS is on, turns on, and the NMOS turns off. When input is 1, the PMOS turns off and the NMOS is on. Okay. So when three inputs are 0, then P1, P2 and P3 are activated while N1, N2 and N3 turn off. So P1, P2 and P3, they are on. N1, N2 and N3, they turn off. If the MOS turns on, then it's represented by the short circuit, and when it turns off, it gets open circuited. Now P1, P2 and P3 they turn on. In this case P1, P2 and P3 they are this is P1, this is P2 and this is P3. This is VDD. N1, N2 and N3 are in parallel, so they are open circuited. And this is connected to ground. The output is obtained from here. This is N1, N2, this is N3. So you can see here all the PMOS they are short circuit and all the NMOS are open circuited. So this passage or this path is completely blocked from these three, and even though the three are in series, all these are short circuited. So path is created here and the output obtained at Z will be VDD, or you can set this as high voltage or 1. So when A is equal to 0, B is equal to 0, C is equal to 0, then the output obtained is 1. So this is the first condition that is satisfied. Now let's see the rest. The second one is when A is equal to 0, B is equal to 0, C is equal to 1. A is equal to 0, this is P1 and 1, this is P2 and 2, this is P3 and 3. When A is 0, P1 will turn on, when B is 0, P2 will turn on, when C is equal to 1, then the NMOS will turn on. So in this case, P1, P2 and N3 they will turn on, then P3, N1 and N2 will turn off. So now these three will be short circuited. This will be short circuited. And this will be open circuited. So P1, P2 they are short. So this is P1, this is P2, P3 is open, then N1 is open, N2 is open, N3 is short. This is ground. P1, P2, P3, N1, N2, N3. This is the output Z. Now, even though P1 and P2 are short circuited, P3 is open circuit. So this will block the high voltage. Then here in N1, N2 and N3, N1 and N2 are open circuit while N3 is short circuit, and N3 is in parallel with N1 and N2, so this is independent of N1 and N2. So the path will be created from here to the output. So the output obtained Z, we can write it as ground or low voltage, let's say 0. So when A is equal to 0, B is equal to 0, C is equal to 1, then the output obtained will be 1. Sorry, this is 0. The output obtained will be 0. Now let's see the third condition. The third condition, when A is equal to 0, B is equal to 1, C is equal to 0. This is P1 and 1. This is P2 and this is N2. This is P3 and N3. When A is 0, then P1 will turn on. When B is 1, N2 will turn on. When C is 0, P3 will turn on. So in this case, P1, then P1, P1, then P3, and this is P3, and N2 will turn on. Then P3, even P2, N1 and N3, they will turn off. So this is represented by short circuit. It's P1, P3 and N2 when they turn on. Then this is represented by short circuit, and then this by open circuit. So P1, P2 is open, then P3 is again short, N1 open, N2 is short, then N3 is again. This is P1, this is P2, this is P3, N1, N2, N3. Now in this case, P2 will block the flow of high voltage. So in NMOS, N1 is short, it's open circuited, and 3 is open circuited. But since they are in parallel with N2, which is short circuit, then the output obtained will be Z is equal to ground, or let's say it's low voltage or 0. So when A is equal to 0, B is equal to 1, C is equal to 0, then Z is equal to 0. Now let's see the next condition. The fourth condition, when A is equal to 0, and B is equal to 1 and C is also equal to 1. This is P1 and 1, P2 and 2, then this is P3 and N3. C1 is associated with P3 and N3. When A is 0, P1 will turn on. When B is 1, N2 will turn on. And when C is 1, N3 will turn on. So P1, N2 and N3, they will turn on. P2, P3 and N1, they will turn off. So this is represented by short circuit, and this by open circuit. Okay, so now P1 is short, P2 and P3 are open. So P1 is short, P2 and P3 are open. This is P2 and this is P3. Now N1, N2 and N3. N1 is open or it's turned off, while N2 and N3 is on. So this is open circuit, N1 is open circuit, N2 is on, as well as N3 is also on. This is N2 and this is N3. This is the output Z. So here P2 and P3, they create a blocking over here. Here N1 is open circuit, but N2 and N3 are short circuited. So you get a path from here. So Z is again ground or low voltage or 0. So when A is equal to 1, A is equal to 0, B is equal to 1, C is equal to 1, then the opt-in output is 0. In the next condition, when A is equal to 1, B is equal to 0, C is equal to 0. When A is 1, P1 and 1, P2 and 2, P3 and 3. A is 1 means N1 will turn on, B is 0 means P2 will turn on, C 0 means P3 will turn on. So here P2, P3 and N1 will turn on, then P1, N2 and N3, they will turn off. So these three will be short circuited and these three will be open. So P1 is open, this is P1, this is VDD, this is P1 open, P2 shorted, P2 shorted, then P3 shorted. Now N1 shorted, N2 and N3 will be open. This is ground, this is N2, this is N3, this is the output Z. So here, even though P2 and P3 are short circuit, this is a open circuit, so this will block the high voltage even though P2 and P3 are short circuit because they are in series. But here N1 is short circuited, so it creates a path or it connects the low voltage with the output. So Z is ground again, or you can say low voltage, or you can say it's 0. So when A is equal to 1, B is equal to 0, C is equal to 0, then the obtained output will be 0. Now let's see the next condition. When A is equal to 1, B is equal to 0, C is equal to 1. P1 and 1, P2 and 2, then C1, P3 and N3. This is P3, this is N3. When A is 1, N1 will turn on. When B is 0, P2 will turn on. When C is 1, then N3 will turn on. So P2, N1 and N3 will turn on. P1, P3 and N2 will turn off. So this is short and this is open. So now P1 is open, P1 is open, P2 is short, P3 is again open. This is 1, 2, 3. N1 short, N2 open, N3 short. Then certainly there will be a blocking over here and this will flow in the output. So Z is again ground, or you can say low voltage or 0. So when A is equal to 1, B is equal to 0, C is equal to 1, the obtained output will be 0. Now let's see the seventh condition. When A is equal to 1, B is equal to 1, C is equal to 0. This is P1 N1, this is P2 N2, this is P3 N3. When A is 1, N1 will turn on, B1, N2 will turn on, C0, P3 will turn on. So N1, N2, P3 will turn on, N3, P1 and P2 will turn off. So now this is represented by short and this open. So now P1 and P2, if they're off, then this is open circuited, and P3 is on, then short. This is 1, this is 2, this is 3. N1 is on, N2 is on, N3 is open. This is ground, this is VDD, this is the output Z. So here there is a blocking, this blocks the high voltage. Here same N1, 2, 3. 3 is open circuit while these two are short circuit, and they're independent of the third NMOS. So the output will be ground or low voltage or 0. So when A is 1, B is 1, C is 0, then the obtained output is 0. Now let's see the last condition. Last condition, that is when all the inputs are 1. When A is 1, B is 1 and C is 1. So this is P1N1, this is P2N2, this is P3N3. When all are 1, only the NMOS will turn on, that is N1, N2 and N3 will turn on. All the PMOS will turn off. So all this will be shorted and all this will be open circuited. So this is P1, this is the condition of P2, condition of P3. So now this is N1, N2, N3. Ground, VDD. This is Z. 1, 2, 3, 1, 2, 3. So totally all these are open circuited and all these are short circuited, then the output will be again ground. So Z is ground, or can say low value or 0. So when A is 1, B is 1, C is 1, the obtained output is 0. So now all the inputs that are given have this correct outputs. So now let's see the twisted schematic. The twisted schematic diagram of a 3-input NOR gate. This is the twisted schematic diagram. The twisted schematic diagram is done as there are 3 PMOS and 3 NMOS. So draw first the 3 PMOS, then the 3 NMOS, okay. Now just name them as P1, P2, P3, N1, N2 and N3. Now this is the source of P1, this is the drain, this is the source of P2, this is the drain, this is again the source of P3, this is the drain. This is source of N1, drain of N1, source of N2, drain of N2, source of N3 and drain of N3. Now the source is connected to VDD. Okay. Now the drain is connected, the drain of P1 is connected with the source of P2. Drain is connected to source. Now all the 3 drains of the NMOS are connected finally connected with this drain, and this is the final output Z. All these are connected, and this is the output Z. D connected, connect. Now all the sources are connected to ground. Source 1, 2 and 3, all three are connected to ground. The gate of NMOS and PMOS are connected. This is input A, this is input B, and this is input C. So this is the twisted schematic diagram of a 3-input NOR gate. Now this is a very simplified schematic diagram, and we'll draw the layout exactly in this manner. Let's draw the layout from the twisted schematic. Layout from twisted schematic. Layout from the twisted schematic diagram. First we have to draw the 3 PMOS, that is, in magic, the layout, the PMOS is constructed by the N well and then the P diffusion. So this is the N well layer. Then there's a P diffusion layer. We are taking a single P diffusion because in our schematic diagram you can see that the source of the first PMOS is connected to VDD, then its drain is connected to the next PMOS source, then the next PMOS source is connected with drain. So we take one P diffusion so that it's easy to find a common point. So this is the P diffusion layer, or the P diff layer. Then you have the N diffusion layer. N diffusion layer is not taken in a single layer. It's not taken in a single layer because we need 3 NMOS and they do not have, only the drains are shorted. If you want you can even do that, but I'll take 3 NMOS. So this is 1, this is 1, this is the second one, and this is the third one. This is the N diffusion layer. This is the N diffusion layer. or you can write it as NDiff. Okay, now we have to short the gate terminals. So gate terminal is drawn with the help of poly. This is input A. This is input B. This is input C. So this is the poly layer. Now after drawing the gate terminal, next you have to find the source. So this is the first PMOS NMOS. This is the second PMOS NMOS. This is the third PMOS and NMOS. This is the source of the first PMOS, drain of first PMOS, source of second PMOS, source drain of second PMOS, source of third PMOS, drain of third PMOS. Similarly, source, drain, and source, drain. These are the gate terminals that are already connected with the help of poly layer. Then the source of the first PMOS is connected to VDD. It is connected to VDD. Then the source of these three are connected to ground. These are connected to ground. So this is metal 1. Write it later on. So this is the reason why we have taken a single P diffusion, because you need not short source and drain. If you take separately, if you separate this P diffusion, then you have to connect the source and drain. Then here again source and drain. So we have taken a common source and drain. You could have even done with this also. If you place the drain over here, source over here, then that could have been done also. Now all the three drains are shorted. They are shorted with this string. This is the output Z. This is metal 1. This is the layout from the twisted schematic diagram. Now we have to place the contacts here. In order to connect this metal with the P diffusion layer, you have to place a P diffusion contact. It's PDC. Similarly, you have to place over here also. This is a P diffusion contact, or you can write it as PDC. Similarly, we need here the N diffusion contact, we could have taken a single one actually. So these are the N diffusion contact, or called the NDC. Now here we have to place the substrate contacts. This is the P substrate contact, or you write it as PWC, and this is the N substrate contact. This is the you can write it over here, it's the N substrate contact. This is the N substrate contact, or you can write it as the NWC contact. So this is the layout from the twisted schematic diagram. Now let's see the layout from the untwisted schematic. Layout from untwisted schematic. So there won't be any space, so let me not write the heading. Untwisted schematic means directly as there was the schematic. Suppose this is the first anvil, this is the second anvil, this is the third anvil. Suppose these are the anvil, and we'll have the 3 N diffusion layers. This are the this is the N diffusion layer. Okay, now we have to place the P diffusion layer. This is the P diffusion layer. Okay, now you have to place the contact the poly layer, that is from here to here. This is input A, then from here input B, then this is the third input C. Now you'll connect this to VDD. This is connected to VDD. These three are are connected to ground. So this is then this is connected, this is connected. These three are connected. I'm just placing a single line. You have to place the whole layer. This is the output Z, 3 input. Similarly, you have to place the contacts I used to place earlier. Here the PDC contact, then here the N-well contact. Similarly here also the PDC, and wherever you need a contact you have to place a contact. Here you need NDC contact, you have to place NDC contacts. So this is the NDC contact. Similarly in the ground you have to place the substrate contacts or the P-well contact. This was poly. This is metal one. So this is the layout. It doesn't look good over here, but if you draw the layout that is mentioned, that is shown in the next lecture, you can see exactly how to draw it in Magic. That is, you can use the previous cells here for drawing a NOR gate. You need NOT and OR gate. So this should be a 3 input OR gate. So if you have the layout of 3 input OR gate, you need a NOT cell and then a 3 input OR gate cell. So if you have these two, you can construct it. That is, you have 3 input A, B, C, then an output Y, which will act as input. Sorry, this should be OR gate here first, and here it should be the OR gate. Here should be the NOT gate. So the output of the OR Y will be the input to the NOT, and the obtained output Z will be the output of a 3 input NOR gate. So if you have these two cells, 3 input OR and NOT, you have done the layout, then you can call the command get cell in Magic, then the cell name, and then if you type X, then you can see the inner layout. So we can also follow the process of cell instantiation in order to draw the layout of a NOR gate.